Okay, so this is the review session for EGME 4.1, Engineering Economics and Professionalism. So this is the review session for midterm 1. So I took the results off the website, off Canvas, and these were the top 3 topics. So there was a tie in number 3, but I think, probably just by going by reviewing number 1, I think we'll review the other one too. And so the number 1 thing was converting non-standard cash flows. And so number 2 was present worth analysis. And then number 3 is annual cash flow. Right? And so I'll definitely at least cover the first 2 in relatively high depth. And then the last one, I'll kind of go over it quickly and see just how much time is left. Okay? All right, so here we go. Okay, and so the first topic we're going to go over is non-standard cash flows. Okay. Right. And so what I mean by non-standard cash flows is cash flows that don't follow the typical patterns of our usual form. So our usual form, remember, are present sum. Okay. So that's going to be our P. And so our second one is a uniform series. These are probably the 2 that we see the most. Okay. And that's going to be an A. And so the next one that we see is a future sum. F, okay? And then we also have an arithmetic gradient, which is G. And so all of these guys have what I call kind of like standard forms in which they, they normally behave. And so, when you're converting between equivalent cash flows, when they're all in their standard forms, it's usually pretty simple. And so a standard conversion will usually only take 1 step. Okay. And so what I mean by that is that, if you're going to convert between like a uniform series and a present sum, you would only have to look up just one value in the compound interest tables or apply just one of the formulas. And so non-standard conversions will usually take more than 1 step. Usually most time it will be 2. But there might be some possibilities where you might have to apply 3 or more. But usually 2 for everything in this class is good enough. Okay. And so before we actually go through the, how we actually do these, multi-step conversions, I think it'd be useful to just kind of go over what all the standard forms for all of these guys are. Okay, so first let's start with present sum. Okay. So remember, the present sum is defined as a single amount of money that happens in the present day. And remember, in our cash flow diagrams, present day is always going to be year 0. Okay. And so if we have a cash flow diagram that looks like this, okay. Right? So we have 1, 2, 3, 4. And so a present sum will simply be a sum of money that happens in the at year 0. Okay? And so let's say that we have a present cost, and that has a value of P. Okay, and so present really means present, so it means it happens right now. Okay, okay. And so present sums, I think, is a pretty standard way, or it's pretty easy to interpret. And so a uniform series, remember what this represents is a recurring cost or benefit that has the same amount at every single time step. Okay. Okay. And so, we can draw the cash flow diagram for this. Okay. And so let's say that we want to do a uniform benefit. And so this uniform benefit will take place for 4 years. Okay. And so the uniform benefit amount will be given the value A. Okay. And so that will be our uniform series. And so one caveat with the uniform series that I think is a kind of a source of confusion is that if you say you have a uniform series that occurs for 4 years, you have to have a cost, or the benefit or the cost has to occur for every single one of those years. Okay. Okay. And so one of the most common forms of a non-standard cash flow would be like a uniform series that starts sometime later. So maybe it starts on year 3 and goes from there. Okay. And so if you say that you want to convert this uniform series to, like, say, a present sum, and you say 4 years, that's going to assume that that uniform series happens on years 1, 2, 3, and 4. Okay. And so this is really the standard form here. So when you come across a uniform series that doesn't that doesn't start at year 1, then that's an automatic cue for you that it's going to be a non-standard. Okay. Okay. And so really and I'll stress this throughout this review session too, that whenever you're doing these cash flow problems, present worth, annual cash flow, even just straight up just computing equivalent cash flows, I really want you guys to draw the cash flow diagram, because a lot of times I think it's really easy to get lost in the verbiage and the numbers of a problem without really knowing what they really mean. So by drawing the cash flow diagram, you really can see what cash flows are standard, which are non-standard, and what you need to do to perform the conversions. Okay? And so really, cash flow diagrams, cash flow diagrams, cash flow diagrams. That's kind of the I'd say that's kind of the pro tip for this unit at least. Okay. Okay. So that's uniform series. So now let's do future sum. Okay. And so future sum is just a single sum of money that happens at some point in the future. Okay. So we can draw a cash flow diagram. Okay. And so we have a future benefit right here. Okay. And we'll give that the symbol F. Right. So future sums are also pretty common. So these will be things like an overhaul cost or like a future salvage value. Okay. And so these are usually pretty easy to move around because they're, just a single sum. The thing you have to be careful about, and this goes for present sums too, is converting between future sums and a uniform series, because you want to make sure that the period's right. But we'll go over that kind of in more detail later. Okay. And so the last one that we have is an arithmetic gradient. And arithmetic gradient, what this represents is it's an increase or decrease in a recurring cost or benefit. Okay. And remember the question from problem 2. So in homework 2. So in homework 2, I asked you, why is it that the standard form for the arithmetic gradient starts on year 2, right? Right. And so let's say that let's use purple. Okay. So the standard form for something that might be increasing would be something like this, okay? Where each increase goes up by a factor g. Okay. And so the reason, arithmetic gradient starts by standard on year 2 is because the G only represents strictly just an increase and a decrease in a recurring cost or benefit, okay? And so if you go back to our standard form for the uniform series, the uniform series starts on year 1, right? And so year 1, you can kind of think of this as kind of the base value or the base amount for a recurring cost or benefit. And so any increases or decreases that occur can't occur until year 2, right? And so when you have a cash flow that starts at a certain amount at year 1 and then increases or decreases from that, then what you would do is you would set the initial amount in year 1. That's going to be your uniform series amount, and then starting in year 2, however much it's increasing, that's going to be your arithmetic gradient. Okay. Okay. And so those are all the standard forms for all of our different cash flows. So there's 4 of them. And so, the subject for this part here is non-standard conversion. So let me just do it. I think, the easiest way to do this is with just a couple examples. Right? And so I'll do a couple examples of ones that you will see kind of quite commonly. You saw these in the homework, or we might have seen these in the lecture. Okay. And so I think, once you start doing 2 or 3 of these examples and you see, the different steps that are involved in converting it, then it becomes a little bit easier. Okay? And so first, let's do a non-standard uniform gradient, a non-standard uniform series, and convert that to a present sum. Okay? And so I'm going to go pretty slow on these examples. So I'm going to show you kind of step by step with several cash flow diagrams. So I think if you see kind of all the steps in between, it really clicks and it kind of makes a lot of sense on why you would do these the way you do. Okay. And so if you're doing an exam, you're doing a homework, and you have to draw these multiple cash flow diagrams, I would say go for it. So I know the cash flow diagrams, they take a little while to draw, and then they take up a lot of space, but really it's really worth it, because a lot of times, it's really hard to see what's going on if you don't draw all the cash flow diagrams. Okay. And so this is a situation that you saw quite often in the last homework 2. Okay, so say we have a cash flow diagram that looks like this, and let's say that we have a uniform series here that starts on year 3. Okay, and we'll say that this has the value of A. Okay, and so what we want to do is we want to compute the equivalent present sum form of this. Okay. Okay. And so first, the first thing we have to ask ourselves, like, is this a non-standard problem, right? And so we can see clearly right here, we have a uniform series because we have a recurring benefit, that's the same amount every single year, okay? But it's not in our standard form, because remember, our standard form for our uniform series is that it starts on year 1, right? So obviously this one does not start in year 1, and so this is going to be non-standard, okay? Okay, so let's do this in 2 steps. And so the first step, that's, whenever you have a recurring type of a cash flow, so it could be either an arithmetic gradient or a uniform series, is to convert that into a single sum. Okay. And the reason you want to do this is that single sums are you know, if your end goal is a single sum, converting a recurring cost or benefit to a single sum, it doesn't have to be in year 0. In this case, it's not going to be. So converting it into a single sum at some point in your cash flow diagram will, you know, help you immensely. Okay. So in this particular case, we have a uniform series that starts in year 3, and so you know, and it goes on for 3 years. Okay. And so let's convert this uniform series into a single sum. Okay. And so the way that we're going to do that is we're going to do A, which is our amount, and then let's convert it into a present sum, but you know, but it's not a present sum that occurs in year 0. It's going to be a present sum that's relative to this uniform series. Okay. And so we're going to do P over A. Okay. You know, let's just say that we have an interest rate. It doesn't really matter. So let's say we have an interest rate of 6%. Okay. Okay. And then we have an N of 3 years. Okay. Okay. Because remember, this goes on for 1, 2, 3, right? And so remember, the length of the uniform series is always given by how many times the cost recurs. It recurs. Okay. Okay. And so if we do this, this will convert this uniform series into a single sum, right? But remember, the standard form for uniform series starts in year 1 right here. Okay. And so if we convert this uniform series in green to a single sum, it's going to start on the year before the recurring stuff occurs, right? And so in this case, the year before the recurrence occurs is year 2. Okay. And so if we apply this conversion here and we draw the new cash flow diagram, okay. If we draw the new cash flow diagram for this, after we multiply by this P over A 6% 3, all of these recurring cash flows in years 3, 4, and 5 become a single cash flow in year 2. Okay? Because remember, year 2 is the year before the recurrence began. Okay? And the value for this is given by what's in these parentheses right here. Okay. Okay. And so now we have this as a single sum, but you know, we're not done yet because we wanted to convert it to a P. Okay. P always happens in year 0, and this is like overall P. Okay. So I know that we use a P over A factor here, but this P over A factor that we use here was simply just to convert a recurring benefit into just a single sum. Okay. And so what we have now is a single sum in year 2, and then in order to complete this problem, we need to take the single sum and we need to transport it back into year 0. Okay. And so another way that we can look at this is that this is a future sum of money in year 2, and then now we can transport it back into year 0 using another conversion factor. Okay. All right, so actually let me use colors here to make it a bit more clear. Okay. And so to transport this back into year 0, we're going to multiply again by another factor. Okay. So step 2. Okay. Okay. And so I'm going to do that on the next page. Okay. Okay. And so let me write out what we have so far. So what we have so far is A, P over A, 6%, and 3. Okay. So remember this, what this did was it transformed that uniform series into a single sum in year 2. And then to take this back 2 more years into year 0, you know, we have to multiply by, my stylus will cooperate. Okay. And so since this is a future sum that we want to convert back to the present sum, we multiply by P over F, 6%, and then 2. Okay. And so now if we draw the cash flow diagram for this, zero, 1, 2, 3, 4, 5. Okay. And so by applying this P over F factor right here, we've taken that single sum that was in year 2 and we transport it back into year 0 right here. Okay. And so this full thing, this is our solution right here. And so you can see, you know, when you have a non-standard uniform series, it's going to take you these 2 conversion factors in order to convert that. So first step is to take your uniform series and over however many times it recurs, and you convert that into a single sum. Okay, and so that single sum here is in year 2, right? And that once you have that in year 2, or whatever future time that you have it, then you bring that future sum back into year 0 with a second conversion factor. Okay? And so, the process, again, that we went through was we took our recurring cost or benefit, we transformed it into, a single sum. We took that single sum and we transported it back into the present day. Okay? And so that's what it looks like for a uniform series. But you can do the same thing for an arithmetic gradient too. Okay? So let's say we have something like this. And non-standard arithmetic gradients are pretty tricky, so it's it'll be good to see this in action. Okay, and so let's say that we have a cash flow that looks like this. Okay. Use a different color. Okay, so let's say that we have a gradient amount right here. Okay, and then the height of this guy is g, right? And so if we want to convert this back into the present day, first thing we would do is we would take this recurring type of cash flow and then convert it into a single sum. Okay. And the first thing we do is take g. We do p over g. Okay. Let's just say that we have 6%. Okay. And now the question here is how many years do we use to do we put for this gradient? Okay. And so the tempting thing here is to say that this gradient occurs for 3 years, and so let's put 3 right here, right? But that would actually be incorrect. Okay. And so the reason for that is because, remember, arithmetic gradients, they start on year 2, and so actually the entire period for this gradient right here would be 4 years. Okay. Because we don't count the first year that it occurs, and then we start counting from there. So this actually occurs for 1, 2, 3, 4 years. Okay? And so we apply that same logic to this guy right here. We can say that this arithmetic gradient occurs for 1, 2, 3, 4 years. Okay? And so that's why we have 4 right there. Okay? And then what that'll do is that it'll take that arithmetic gradient and then it'll transform that into a single sum on the standard form of where it would be created. Okay? And so since this thing starts in year 3, okay, transporting into a present sum would be, or applying this p over g factor would transform it into a single sum on year 1. Okay? And so if we want to take this back to year 0, we apply the same thing we did up here to p over f, 6%. But since this is in year 1, then we're going to do 1 year just like that. Okay? Right? So be really careful when you're transforming a non-standard arithmetic gradient back into present sums, because you have to take into account that arithmetic gradient start in year 2. Okay. Okay. And so as you can see from this example right here, what I did was I really took the time to draw out kind of these intermediate cash flow diagrams that help me kind of visualize how things are transforming. So, I think if you kind of take your time with these kinds of problems and really draw out the cash flow diagrams for every step, then there's no way you can, or it's going to be a lot easier to figure this out from start to finish. Okay. Okay. And so that's, if you take a recurring cash flow and you transform it back into a single sum, now let's go the other direction. So I think the other direction is also a little bit confusing. And we saw a little bit of that in the last lecture notes for annual cash flow. Okay. So one of actually was the last example that we did before we went over amortization tables. Okay. Okay. And so actually the only way that you can get a non-standard transition going from a single sum to a series is actually if it's for a future. So if it's present day is awesome, because from present day you can do kind of anything that you want from there. But for a future, you have to kind of be really careful with this. Okay. And so let's do an example here. Right? And so let's say that we have a single future sum and we have it in year 3. Right? So we'll call this F. Right? And then what we want to do is we want to convert this F into a uniform series that spans all 5 years. And so, I'm saying it explicitly that the uniform series spans all 5 years, but most of the time this is kind of implied. So like if you're doing like an annual cash flow analysis, it assumes that your time period is going to extend over the entire period. So, I'm saying explicitly here, but if you're encountering this in a problem where you have to compute like the EUAW or any kind of uniform series or gradient, just assume that whatever you want to compute in the end is going to extend over the entire series. So we want to convert F to, let's say, just a uniform series for now. Okay. Okay. And so the tempting thing to do in this problem is to just say, hey, we have a future sum, occurs at year 3, and so let's just apply an A over F factor. So we can say that A is equal to F times A over F. Okay. And again, we're just using 6%, but this applies for all other ones. Okay. And since this occurs in year 3, let's put 3 right there. Okay. But what you're actually doing in this case is converting a standard F, which is assumed to occur at the very end, into an A, which only will occur for up to that. Okay. Because remember the key number here is this 3. Okay. So remember the standard form from a uniform series is that it spans up until the number n that you specify for your problem. Okay. And so if we actually perform this conversion up here, what's going to happen is that we're going to have a uniform series, but it's only going to go up to year 3 because that's the amount of time that we specified here for the conversion. Okay? And so obviously this is not what we want because it's a uniform series, yes, but we're missing the contributions on year 4 and 5. Okay? And so this is another example of a non-standard cash flow where you would have to apply more than one conversion. Okay? And so this is not what we want. And so on the next page, I'm going to show you basically how to do this, which again, it's going to involve multiple conversions. Okay. Okay. And so let me draw the cash flow diagram again. Okay. And then let's draw our future sum. Okay. And so in order to have this uniform series span the entire 5 years, we need to do multiple conversions. So, just like we did from before, the easiest thing to do is to utilize those present sum formulas. So first, let's convert this. Into a present sum that occurs in year 0. Okay. And so the first thing that we're going to do, let's say that P is equal to F times P over F, 6%. Okay. And we're going to transport this back 3 years. Okay. And so if we draw the new cash flow diagram after performing this conversion, okay, it would look something like this. Okay. All right. And so, at first it might seem like, we just moved the arrow from one place to the other, but we're in a much more advantageous position here because we have P that occurs, at the very beginning of the period, and this is a standard P. So this is, with this P we can do whatever we want with it. Okay? And so to convert this into a uniform series that spans all 5 years, let's say that we have A, okay, is equal to P. We just multiply by A over P. And so if we write out the entire expression here, okay, we just plug in for P. because we know that P is equal to F up there. So say that A is equal to F times A over P times P over F, 6%, 3. Okay, and so yet again we have an expression with multiple conversions. Okay, and then the end result is something that looks like this. Okay, and then the end result will have a uniform series that looks like this. Okay, and this is exactly the form that we want for this problem, right? Because we wanted a uniform series that spanned all 5 years. Okay, so these two examples basically show you, two of the kind of broad categories of non-standard cash flows that you would encounter. And so, the tricky thing is always going from, our single sums, which are present and future sums, and our recurring cash flows, which are the uniform series and the gradients, and kind of exchanging between the two when they're not in a standard form. But if you kind of do this kind of process where you convert, present sums are always awesome because you can kind of do whatever you want with that. So first you convert, it to some kind of present sum. You either take the uniform, you take the recurring cash flow and you convert it into a single sum. And then from there you can, transport it back one more time. Or you take a single sum, you bring it back to present day 0, okay? And then from present day 0, you can spread it out however the heck you want. Okay? And so these are just kind of two examples on how you deal with these non-standard cash flow problems and the steps that you can do to perform their conversions. Okay? And so remember, for these non-standard ones, you have to do at least two conversions and draw the cash flow diagrams to help you kind of step by step along the process. I think with that, a lot of these problems become a lot easier if you do that. Okay, so that's non-standard cash flows. And so the next thing that that was requested to go over was present worth analysis. Okay. And so the idea with present worth analysis is that, up to this point in the class, we'd spent a long time on that first lecture notes on, what does interest mean? What are these different cash flows? How do we convert between them, right? So we spent a lot of time, doing problems like we did just previously on how to do that, okay? And so present worth analysis is kind of our first chance to actually apply this for some real actual, decision making in engineering, okay? Because one problem or one issue that you'll have very commonly for engineering projects is that you need to decide which option to buy, or like which vendor to go with, or which materials to buy from a list of options. Okay? And so present worth analysis is a way to it's a type of economic analysis. Okay? And it's used to determine the best economic alternative. Oops, got ahead of myself. And so in all these present worth types of problems, I'm going to present you with at least two options. So you need at least two. Sometimes it's going to be 3, sometimes it's going to be 4. And then what you're going to do is you're going to compute the present worth. Okay? And so the present worth is nothing more than just all the cash flows in the problem converted to a P. All right, maybe I shouldn't say problem. Maybe I should say all the cash flows within a certain option. Okay. And as we've talked about before, if you have all the cash flows in your problem in the same form occurring at the same time, which is automatically satisfied if you have a present sum, because the present sum always occurs in year 0. If you have all your cash flows happening at the same time in the same form, then you can just simply add them up. Okay. And then once you've added up all the cash flows in present worth format, then you'll get a single number that describes the economic efficiency of that option. Okay. Let's see. And so that's kind of the crux of present worth analysis. And so a lot of times the way that you're going to go about these problems is, you have your different options. You're going to list out all the cash flows. You can, just like, we saw before, drawing the cash flow diagram would really help. And then from there, you compute the present worth, and you do that for every single option, and then you pick the one that's the best. Okay. Okay. And so before we kind of jump into some of the problems and some of the caveats, let's talk just a brief little bit about how do you interpret these results. Okay. Remember, the present worth of something, or the present sum of money of something, is money that you can have on hand right now. So it's either money that you're going to pay out from your wallet, or money that someone's going to give you right at this minute. Okay, and so the way that you interpret present worth is that it takes all the cash flows that are going to happen over over the course of the project, all the maintenance costs, and what the present worth represents is, if you decide to go with this option, this is how much money that someone would write you a check for at this very moment, either that they would pay you, or you would write a check for in this very moment, and it would be subtracted from your bank account right now. Okay. And so this is a little bit different from annual cash flow, where annual cash flow is kind of how much it would be worth, each year if you were making a recurring payment over a certain amount of years. Okay. Okay. And so just let's do a very simple example. Actually, let's do one from the homework. I think that would probably be best. Pull it up. Okay. So I think kind of the simplest example for this would be like problem 4A on the homework. Okay. And so 4A, I present you with 3 different options, and what these 3 different options represent are 3 different configurations for a sports gym that you're thinking about investing in. Okay. Okay. And so let's list out the cash the cases. Okay. So we have A, B, C. And so we have our initial cost, which is the construction costs. Right? Right? And then we have the expected annual revenue. Okay. And so, before we start filling in numbers here, let's categorize these types of cash flows, because they're all going to be the same. Okay. And so the initial costs, this is something that you're going to pay up front. And so this can be a present sum. And then the annual revenue, because since this is the amount of money that you're going to make every single year, this is going to be a uniform series. Okay. So the initial cost for option A will be $525,000. And so the initial cost for option B is $680,000. And then the initial cost for option C is $825,000. Okay. And so in terms of annual revenue, option A will make you $125,000. Option B will be $145,000. And option C will be $155,000. Okay. And so if we assume an interest rate of 5%, And then we have a analysis period of 20 years. Okay, all of these guys are 20 years. Okay, and so we want to compute, or we want to determine which is the best option to go with. Okay. Okay, and so what we're going to do is we're going to compute the present worths for each of these different options here. Okay, and so luckily for us, all of these they have the same form. Not only do they have the same form, but they're also all standard, so we don't have to do any kind of non-standard stuff. Okay, and so the present worth of an option will just be, remember, we're converting everything into a P. Okay, and so we have two cash flows. So the first one is our initial cost. So we have minus initial cost. Okay, and then to that we're going to add our revenue. Okay, but since our revenue is a uniform series, we need to apply a conversion in order to bring this into present day times. Okay, so this is going to be P over A. We have 5%, and then 20. Okay, and so all you have to do in order to compute the present worths is just plug in these values, one from this table, and then for this guy you plug in from the compound interest tables. Okay, and so if you do that for all three options, what you get is the present worth of option A, which is 1,032,750. Okay, and so what that's telling you is that if you invested in option A, then it'd be like if someone just handed you a check for $1 million and $1,032,750. Okay, and so for option B we have 1,126,990. Okay, and then for option C we have 1,106,610. Okay, and then we can see from this that the one that's the highest here is B. Okay, and so what we say is that option B is the best. All right. And so when you're doing these present worth problems, remember, ultimately the thing that's most important is this decision right here, right? Which option to go with. And so, I kind of let it slide a lot for the homeworks because, it's your first time doing it, but I want more than just, you computing the present worths for every single option here, okay? And so what I want you to do is to not only compute the present worths, but use those present worths to actually make a decision. And in this case, the decision is that the present worth of B is the best option, okay? Okay. And so that's that's kind of the basics of present worth. So I mean, it's basically just an application of a computing equivalent cash flow. So you convert everything into a present sum, do multiple conversions if you have to, if it's non-standard, and then you get a single number, and then you compare that to all the other ones. That's really all there is to it. And so let's throw a little bit of a wrinkle into it. Okay. And so the first wrinkle that that might occur is if you have a situation where the time frames are not the same. Okay. And so because you're converting everything into a single sum of money in the present day, what that in order for you to kind of do a fair comparison, you have to compare two different. You have to compare your options over the same horizon. Okay. And so if you're doing a present worth problem and you see, something that doesn't have the same period, so you have, one option might last like 6 years, and another option might last 9 years. Okay. In those cases, you can't just straight up just compute the present worths using their own time periods. Okay. Because in that you'll get results that are not reliable at all. Okay. And so in order to analyze these cases where the time periods differ, you need to be able to make it so that their time periods are the same. Okay? And so there's two ways to do this. And so the first way, is the least common multiple approach. Okay. And so the least common multiple approach, what you have to do is you take all the project lives that you have for everything in your problem, and then find the least common multiple among the project lives for all the different options. Okay. Okay. And so once you've computed the least common multiple, what you need to do then is you need to extend all of your project lives to match this least common multiple. Okay. And so, when you do this, obviously you're going to run into situations where, your projects or your products are not going to last the entire time, because, whenever you buy a product, they say, this product's only going to be good for 3 years. Okay. And it's not like the eggs you have in your fridge too, where you can say like, I'll use it past the expiration date. A lot of these entering machines, they're really only designed to last for a certain amount of time. And once they're done, then, you have to really, buy a new one. Okay. And so for cases where you have to extend the life, what you have to do is that every time you have a product that lives over the course of its life, you buy a new one. Okay. Okay. And remember, kind of one of our key assumptions here is that the replacement that we buy at some point in the future, first of all, we're going to assume that the replacement will still be available, which might not be true. You buy it, you try to buy a 6-year-old pump. 6 years later, it's going to be tough. Okay, and so we assume. So we'll assume that we can get the exact same part or exact same product. We'll assume that we can get the exact same product, and that the product will cost the same as it did when we first bought it. Okay. All right. And so that's what we'd do. So let's kind of do an example for this. Okay. And I'll just kind of make one up right now. Okay. And let's say that we want to determine which machine to buy between two different machines. Okay. And so let's say that machine A we'll say that machine A has an initial cost and so just to kind of avoid putting numbers here, I'll say the initial cost is PA, okay? And this machine, you know, once it starts producing product, it'll make you a revenue of AA. And so in addition to that, you know, we'll say that we can salvage it at the end for FA. Okay. And then we'll say that product A will last 6 years. Okay. Okay. And so that's product A. And so let's go over product B. Okay. And so product B, we'll assume that the cash flows are going to be the same, just as in terms of the same types. So it'll have an initial cost, it'll produce a revenue, and it'll have a salvage value. So, but they're all in the B form. Okay, so we'll say there's PB, AB, and FB. Okay, PAF. Right. But instead of lasting 6 years, we'll say that machine B lasts 9 years. Okay. Okay. And so, you know, we want to use present worth analysis to determine which machine is better, right? And so, you know, obviously, you know, we don't have numbers here, so we won't be able to determine exactly the present worth, but we can at least set up the equations and set up the cash flow diagrams in order to do so. Okay. Okay, so let's draw out the cash flow diagrams for both of these guys. Okay. Well, first, you know, first of all, before we even do that, you know, because we have two products here with different lives, let's compute the least common multiple. Right. And so remember, our two product lives here are 6 and 9, and so the least common multiple for this will be 18. Which I realize now is a huge mistake because there's no way I can fit 18 years onto a tiny iPad like this. But we'll trudge onwards. Okay. Okay. So let's draw the cash flow diagram for A. Okay. So I'll continue on to the next line. Okay. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And so product A, you know, we have an initial cost of PA. So we'll say that we have PA like this. Okay. And product A here will last us 6 years. So, you know, 6 years is obviously less than 18. And so what's going to happen in year 6 is that we're going to buy a new one, okay, at the exact same price, right? And then we're going to go 6 more years. And in 6 more years, you know, we're still not at 18. And so in year 12, we're going to buy another one. So PA, okay. And then from that, that'll take us to over all the way to 18. So at 18, you know, we don't need to buy a new one because we're done using it. And so that's that, okay. Okay, and so next thing we'll do is we'll add in our revenue. And so our revenue, remember, is AA, A, okay? And then the last thing we have is our salvage value, okay? So our salvage value is going to occur basically every time that we buy a new one, because when we buy a new one, or every time that we use up a machine to its fullest, okay? And so we use up a machine to its fullest in year 6, we use up one to its fullest in year 12, and we finally use one up in 18 as well, okay? Okay. And so now that we have this cash flow diagram and we bought all the replacements, you know, we can go ahead and compute the present worth. Okay? And so the present worth of A, and this is really easy to compute based off the diagram here. Okay. And so the present worth of A. So let's start with PA first. Okay. Okay. And so when you have a situation like this where you have multiple single sums that occur at different parts of your cash flow diagram, you know, this is kind of a shorthand notation to kind of save you from writing a ton. Okay? And so since we know that PA occurs 3 different times, let's just say that this PA is going to multiply by 3 different factors. Okay? And so the first factor is just simply 1, or I should say this is minus PA, right? The first factor is 1 because that, you know, that's the one that occurs in year 0. And then to that, we're going to add the P over A, the PA factor that happens in year 6. And so in order to transport this back into year 0, we have to do a P over F. And then, I don't think I gave an interest rate, so let's just say it's I. And this will be 6 years because this occurs in year 6. Okay. And then to this, we're going to add the factor that occurs in year 12. Okay. Okay. And so those are all the P over A factors. Next, let's add our arithmetic gradient, or not, it starts with A, so I always think gradient, but this is our uniform series, okay, so this is AA, and this occurs over the entire 18 years, so we don't have to do any kind of non-standard stuff, and so this is simply just going to be a P over A at our interest rate at 18 years, all right, and then finally, we have our future sums, okay, so we have FA. And again, this occurs at 3 different locations. Okay, so that's going to be P over F, I, first one's at year 6, okay, plus P over F, I, year 12, okay, plus P over F, I, and year 18. Okay, and then all you have to do is just plug in values from the tables or plug in values from the you know, from the problem, and then you'll be able to compute this present worth. Okay, and so, you know, now let's do option B. So option B is a little bit simpler. Okay. So let's draw our horizon again. Okay. This is 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Okay. And so first, let's draw our cost first. Okay. And so you know that B lasts for 9 years. Okay. And so after we buy our first one, it's our second one is we need to buy our second one year 9. Okay. But since it lasts for 9 years, that's all we got to do, because the second one that we buy will take us all the way to year 18. So we don't need to buy more than the 2. Okay. Next, we have our revenue. So that's going to be AB. Okay. And then we have our salvage value for FB. And so remember, that only occurs once we sell our machines. Okay. Okay, and so let's compute the present worth of B. And so this is going to follow the same process, right? And so first, let's consider our costs. Okay, so we have a minus PB, and this occurs twice. So this occurs in year 0, so we don't need to do any conversion. and then it occurs again in year 9. So we have P over F, I, 9, okay, plus our uniform series. So we have AB, okay, and this is P over A, I, 18, because it lasts for all 18 years. And then we have FB, okay, and it's going to be P over F, I. First one occurs in 9, okay, and the second one is P over F, I, 18, okay, and then that's our present worth of B, okay. And so what you're going to do from this point is basically just plug in all the numbers and see which one's higher, and then from there you can choose the best one. Okay. All right. So I think those two examples I think kind of encapsulate kind of the essence of what present worth analysis is about. Okay. So I only have a few more minutes, so I think I'll just kind of touch very briefly on annual cash flow. Okay. And so annual cash flow analysis is kind of like the sister to present worth. And so instead of computing everything into a present sum, you convert everything into a uniform series. Okay. And then from there, you can, you'll be able to determine, same thing that you did with present worth. So you convert everything to a uniform series. You compare and see which one's the highest, and you pick the one that's the highest, for your best option. Okay. And so the term that you'll see pretty often in annual cash flow analysis is EUAW. Okay. And so it's a very long acronym, but all it means is equivalent, uniform, annual worth. Okay. And all this is just another name for A. Okay. And so when you see that, don't panic. Okay. And so I don't have time to do an example, but I will tell you kind of one thing that annual cash flow really has an advantage over present worth. And that's in dealing with cases that we just did in our previous example, actually. And so for cases where you're comparing options with different product lives, okay, you actually don't have to do anything special for annual cash flow analysis. So actually all you have to do is just compute the EUAW for the life of one product. Okay. Okay. And so if you do that and you make the assumption and you kind of implicitly make the assumption that you're going to keep buying replacements every time that they're used up, then you don't have to do the least common multiple stuff like all we did right here. And so actually the EUAW that you compute for a product for just its useful life will be the correct EUAW to do. So if you actually go back in our lecture notes, we actually computed the EUAW for a case where we did have a cash flow diagram with the replacement. And what you'll see from that example is that it didn't matter if we included the replacement or if we did it with just just have one product life. And you'll see that we actually get the exact same answer. So, for cases like the previous example where you have, different product lives, annual cash flow is a little bit easier to do. So you don't have to extend the life and you don't have to find the least common multiple and buy replacements and all that stuff. And so as long as you can assume that you're going to buy replacements, annual cash flow is the kind of the way to go for this. Okay. Okay. So I'm just out of time. So actually I have to go into office hours very soon. But hopefully, you guys found this review helpful. And so, hopefully by the time you see this, you'll see this before Thursday night. So you can have about a week to watch this and study for the exam. And of course, with anything, as with anything that we do in the lecture, if you have any questions about the things we went over today, just shoot me an email and I'm always happy to answer them. All right, so best of luck when you're studying.